Okay, today is October 5th, 2021, and that's Physics 37 lecture. Okay, so let's review here again what I said. According to this syllabus, we are going to have a lab today on Tuesday. It's going to be projectile motion and an exam on Thursday. Tuesdays, students are going to have a lab today, but Thursday, students will not have a lab Thursday, okay? And eventually, the Thursday students are going to catch up with the Tuesday students. Okay, so let's just review quickly what we were doing last time. Okay, we're talking about the coefficient, the force of friction, force of static friction, and force of kinetic friction. Okay, now that you know how those two forces behave, we can start solving some problems involving friction. Here are my notes. Oh, here you go. That's the graph that you have to remember. You know, force of friction and applied force. Applied force, okay? The force of friction coincides with the applied force up to a certain value, up to a maximum value. When you have a force of static friction, the object is at rest. When you exceed this maximum value of the force of static friction, there is a relationship for it. The force of friction, the object starts moving, and what was force of static friction now becomes force of kinetic friction. In general, the force of kinetic friction is less than the maximum value of the force of static friction. It may be equal to. Okay? And there is a relationship that you have to know for those forces of static friction. Right in here. Here you go, force of kinetic friction. Both force of kinetic friction and the force of maximum value of the force of static friction, they depend on the normal being applied to the object, the normal force. Okay, so here you go. See that? The maximum value, normal as well. And the coefficient, the equations are similar, it's just the coefficient is slightly different. One is for the coefficient of static friction, the other is for the coefficient of kinetic friction. Okay? And notice that the force of static friction has a range of values. It doesn't have a single value, it has a range of values. Whereas the force of kinetic friction has a single value. Okay? So let's put the date here. I'm going to write that down. Add, insert. Go. Today is October 5th, 2021. Right? So today we have a lab. Thursday we will have an exam that starts at 7 p.m. For this reason, there will be no lab on Thursday. Okay. The exam window is 24 hours, and you must pick 2 hours within this window. The latest that you can start is 5 p.m., right? Or the following day. The latest you can start, you can start to take full advantage of the 2 hours is 5 p.m. October 8th, right? The exam starts on October 7. The window of the exam starts on October 7 and closes October 8th. at 7 p.m. Our review, right? Last time we were talking about the force of friction. There are two forces. There are two forces of friction: static and kinetic. Okay. Differences between them. Differences between them. One, force of static friction occurs when the object is at rest. Okay, versus kinetic friction, which occurs only, right, when the object is at rest, versus kinetic friction, which occurs only when the object is moving. And that has to be moving with respect to the contact surface. Okay, that's what it means. That's what it means. Moving with respect to the contact surface. 2. Force of static friction has a range of values from 0 to a maximum value. Force of kinetic friction has a single value that depends on the coefficient of kinetic friction and the normal. Okay, those are the differences. What else I can put another difference. Okay, 3. Force of static, not force of static friction, the maximum value of the force of static friction is usually greater than the force of kinetic friction. Those are the differences, right? Similarities. Okay, 1. Opposed motion of the objects. Okay, maximum value of the force of static friction depends on the normal, just like the force of kinetic friction. The maximum value of force of static friction is also a function of a coefficient of friction. I'm going to put it here, coefficient of static, right, friction. But remember, it's the maximum value, so those are the similarities. And those are the differences. Now we can start talking about solving some problems. Let's go get PowerPoint here, my drawings. I didn't do any example last time, right? I didn't do any example with friction, right? No? Okay. Let's see here. Let me see if I have one here. Force of friction, yeah, okay. Okay. And those are the notes. Let's review the forces. Forces reviewed so far. Forces reviewed so far. What's that? The first one was what? The weight, right? Right? What was the second force that we talked about? What was the second force we talked about? Normal. Okay, then we talked about each other. Here you go, and let's make a demonstration, right? Here you go. Here you go. Do you see any force here other than those two that I mentioned? I can hear you. Tension, yeah. Here you go. Tension. Tension. And then that was all, right? We didn't have any other force, right? But there are more, okay? But for now, I don't want to overwhelm you with too many forces. Now, force of friction, static and kinetic. There are more. So remember that. Let's keep on introducing them little by little, so you don't have to burn your head memorizing a bunch of things at once, right? So here you go. Let's take a look. Let me take a, let's see. Maybe I don't want to do that now. Maybe I want to do something simpler. Let me check here. Lecture. Maybe this two. Maybe this one here. Okay, I'm running out of power. Let's connect it before I run out of juice here. Good. I need to break down this PowerPoint in several sets of the slides so I don't have to keep on shuffling from one slide to another one. I believe I have what, 500 slides here. Motion, go to the motion. Okay, yes, projectile motion. This one is what? Yeah, I think I know that is. Okay, circular motion. Okay, this is relative motion and forces, right? Take a look at this one. Tension. I put an applied force there. frictionless surface, frictionless surface. Okay, now, yeah, let's do this one here. Concurrent slide. Let's take a look here. Okay, so we have this object at an inclined plane. We know the angle, we know the mass of the object. Hey, wait a minute. If it's frictionless surface, then let me see here. Okay, if it's a frictionless surface, then you cannot calculate the static force, force of static friction. Okay, so let me just correct that. Yeah, if it is, I'm gonna do the following. 271. Okay, so here we go. Paste. I gotta fix those slides. Okay. Okay, this one is a frictionless surface, so forget about that. Don't calculate. Yeah, a frictionless surface. Don't calculate the force of static friction. Okay, now we're going to calculate the force of static friction. And what else you need to know? You need to know that the object is at rest. V is equal to 0. Ooh, too small. Ooh. That's, oh. Is there any way to shrink this panel? There must be, I think there is a way. Oh, here you go. Yeah, here you go. Now let's zoom in. Okay. V should be lowercase v. Okay. Calculate the force of static friction in this case. Okay, how do we do that? Okay, we know the angle. Okay, V is at rest. Oh, it's not a frictionless surface, right? Otherwise, the friction would be 0. It's not a frictionless surface. Okay, this was a different lab elsewhere. Here you go. We gotta choose we gotta identify the forces. We gotta identify the force. We know that we have the weight. We know that we have the normal. It's not a frictionless surface. There's no other force applied to this block. So we must have another force here that doesn't let the block move. And this force is going to be what? If there's no friction, the block is going to slide, no matter what. But if I'm telling you that the block is at rest, that's because there must be another force there. And this force is probably interesting. Let me see what's going on here. Let me copy this one. V equal to 0. Whoa. Here you go. V equal to 0. V equal to 0. weight, normal. Let's not forget to put v equal to 0 there. Here, v equal to 0 as well. Keep it complete, right? Yeah, 0, 0. So there is one more force that's missing. What's the name of this force? Huh? If the object is at rest, there must be a force canceling this component of the weight. It's this component of the weight that's going to propel the block downhill if there is no friction. But if there is friction, we must have a component, a force of friction canceling out this component of the weight. It's going to be like that. More or less the same value. It's not going to be necessarily equal to the maximum value of the force of static friction. And I'm going to put it in a different color. Okay. Go. Ooh. Yeah. And I'm going to label it as F sub S. Remember, this is not a lab. This is a lecture, right? So I gotta fix that as well. Here you go. F sub F. Good. I'm going to put it. No lab. This is not a lab. All we want is to calculate the F sub F S in terms of the other forces. Okay? So let me copy that and put it in the next slide. Here you go. First thing that you gotta do, you gotta put the X and next thing that you gotta do is have to put the X and Y axis there. For a system like this one, you are better off put a X axis that's parallel to the ramp. Okay? Don't forget to put the force here, right? I am suspecting that this y-axis is not exactly perpendicular, is it? Somewhat. Almost, right? Oops. Oh, here you go. Those mouse pads are so terrible to use. Here you go. Is that perpendicular? Let's see if it's perpendicular. It's a little bit off. Let's. Okay, now it should be perpendicular. Okay. X and Y axis. We have okay. What am I doing here? I'm breaking down the weight in two of its components. Okay. So you can identify what are the angles that are involved here. You did a similar problem before, right? Let me finish all the axes here. Good. And then we This one I'm gonna get rid of the other one. Ah, okay, that's the one I want to get rid of. Good. Get rid of both of them and then good. Yep. Get rid of both of them and then paste what I have in my buffer here. Good. Now you have it. Perfect. And now we can start putting back my force of static friction there in this problem. Okay, here we go. So what we have to do, we have to identify that angle. At this point in time, you should know that, right? This angle is theta. If this angle is theta, then this angle here is 90 minus theta. Okay? If this angle is 90 minus theta, so this angle too must be 90 minus theta for this right angle triangle. This right angle triangle is similar to this other right angle triangle. So which implies that this angle here must be theta. Did I label it? No, I didn't. Oh yeah, I did label. And let's put it here. Okay, so here you go. This angle is theta. Okay, and I mentioned to you that the object is at rest. So this guy goes away. This is no longer a frictionless surface, right? Here you go. Get rid of all frictionless here. Get rid of all frictionless. There is no acceleration because if v is equal to 0, there will be no acceleration whatsoever. And we are going to have this force of static friction. Okay, so let's play the movie. That's what I call playing the movie. This one right in here. Calculate f sub x. Slideshow. Here you go. From current slides. Here you go. We have a mass sitting over a surface, inclined plane. The plane makes an angle theta with horizontal. The mass is at rest. Okay, we want to calculate the force of static friction. How do you determine that? Okay, we identify the forces, weight, the normal, and the force of static friction. The block is not moving anywhere. And then what do? We put the axis, x and y axis. For this specific situation, it's more convenient to set the x-axis parallel to the plane. But you could solve this problem with this regular axis as well, okay? You might want to do that on your own there at home. And I am breaking down the forces, the weight, the components of the weight in this new coordinate system. And I am identifying the angles. Here you go. We have this right angle triangle, right? And we have this other right angle triangle. In this right angle triangle, this angle is 90 minus theta. Consequently, this angle is 90 minus theta, and consequently, this angle must be theta as well. So Wx must be equal to mg sine of theta, and Wy should be equal to mg cosine of theta. Okay? So let's set up the equations now. Notes. Okay. Look at the drawings. Look at the drawings in PowerPoint. PowerPoint. I'm going to take advantage of the previous equations that I have there. The object's at rest, consequently the net force applied to the object must be equal to 0, Newton's first law of motion. Man, this is so slow. It's going to take forever. Oh gosh. I can't stand it. Okay, okay, I gotta get the first, yeah, it's gonna take forever. I'm gonna get this one here. And drawings in PowerPoint, you know, net force is equal object at rest. Object is at rest. Consequently, net force is equal to 0. Here we go. And I'm gonna put in vectorial format. Take your time. Oh man, I miss my big computer there at home. Nope, that's not what I want. Gotta do that again. It's this one that I want. Yeah. Good. Okay, net force is equal to 0. Okay, which by the way ends up being what? The weight, the normal, and the frictional force. The weight, the normal, and now I'm gonna use the frictional force, and should be, I'm gonna put it lowercase f because that's how we denote. Ooh, I wanna keep the, yeah, here we go. No, what's going on here? Okay, that's what I, good, now it should work. S. I'm not gonna put maximum, I'm just gonna put force of static friction. Okay? Because the object is at rest, that should be equal to 0. And those forces can be broken down into two components, x and y. Okay, x component. W, x, and now I don't need the arrow at the top anymore because I'm dealing with scalars. And here I'm going to emphasize that it's the x component of the static force. Net force in the x direction. Okay, and then I'll do the same for the y. net force in the y direction. Y component, oops, no, capital, lowercase, y component and y component. Okay. Going back to the drawings, let's see what's the value of each component. Going back here to the drawing board. Okay, the Wx is sine of theta, mg sine of theta. Mg sine of theta. Sorry if I don't make eye contact with you folks, but sometimes I get so concentrated on this thing, I don't have time to make eye contact, okay? So here you go, let's go back to the drawing again. Do you have, does the n has an x component, yes or no? Does the normal has an x component? I can hear you. No. Okay, so we can make it equal to 0. This one here, right? Emphasize that it's 0. And the force of static friction does have x component. Right? Take a look here. Does have an x component. Now let's worry about the y components. The weight is down. And by the way, this Wx should be minus mg, right? I didn't put that minus mg. It should be minus mg sine of theta. And this one should be minus mg cosine of theta, the y component. So minus mg sine of theta here. And the other one is minus mg cosine of theta. Then y component is going to be, in its integrity, is going to be equal to n. And there is no y component for the force of static friction. There is no y component for the force of static friction. What we find out? We found out that in order to determine the force of static friction, we need only the x component of the weight, because the x component of the normal is 0. Okay, so here you go. Okay. And if we want to go the next step, we can also, I didn't ask you for that, but we can solve for the normal as well. I didn't ask you to solve that, but okay, so here you go.
Professor?
Yeah.
For the net force of y, should that be negative mg cosine theta?
Yeah, let's take a look. Let me put lowercase y here. Let's take a look here. Okay, look at this component of the weight, right?
Right.
Is it parallel or anti-parallel to the y-axis?
Parallel to the y.
Anti-parallel.
Okay.
Y is pointing
Pointing in
upwards.
just the opposite direction.
Yeah, opposite direction, anti-parallel, right? That's why we have a negative. Okay.
But should it be cosine instead of sine?
Yeah, it's cosine, see?
I think you wrote
Did I
sine.
put, let's see. Maybe I didn't correct it, right? The y, oh yeah, that's right. I skip it, cosine, yeah, thank you. And this one should be cosine, yeah. But you understood the negative sign, right? It's negative for both directions, x and y. Thank you. Okay, so we calculate, that's one way of, now, let's do another one here. We increase the plane to an angle theta prime. Here you go, theta prime, which puts the block on the verge of motion. Okay? which puts the block on the verge of motion, just about to move. Okay, this is something that we can illustrate here. I believe I did that before, right? You know, it's an experiment that you can do in the lab. Here we go. Oh, I don't like that. Let's see. This one? Nope. This one? Let's try this one. Okay, I'm going, here you go. This block's at rest, right? And little by little, I'm going to increase the angle. Because of we have a force of static friction here, the block is not sliding, right? But eventually, it breaks free and starts sliding. That's the point that I call verge of motion. Okay? Right now, it's gonna, that's not what I wanted to do, but it comes to a point that it's going to slide. Let's see. Yeah, right in here. At this very angle around here, the block is on the verge of motion. Okay? Just before, just a little bit lower than this angle, the block was on the verge of motion. That's something that we're doing in experiments there in the lab. Let's put it. So let's say this angle, theta prime, greater than theta. Okay, I'm gonna put it like that. Theta prime greater than theta. Increase the angle of the plane. Increase the angle of the plane. The angle of the plane to theta prime greater than theta, which puts the block on the verge of motion. Determine the coefficient of static friction. And now I'm asking the coefficient of static friction. Okay. So we're gonna go to our drawing here. Always illustrate. I'm gonna increase the angle. Let's see here if I can do that in an easy way. Hopefully I will be able to do that in an easy way. Did I get it? I'm gonna group it. No, I don't like it. Undo it. I'm not going to group those. I don't want to affect those labels. But everything else I want it to be affected. Not this one. Not this one. Okay, so now I'm gonna group it. Let's see if it works. I'm going to increase. Oh, how do I rotate it? How? Ooh. Yeah, rotate it, right? It's more, right? Now it's definitely more. It's just as this triangle became odd, but I will fix it. This one, I don't want it grouped. Oh gosh, what did I do now? Hate that. Something happened. Okay, good. I don't want those labels selected, so I gotta click that one by one. There's no other way. Okay, X, Y, what else? Okay, I think that's how I have to. Oh, this one I have to click. This one. This one. What else? What else? What else? What else? I think that's all. If there's any other one. Okay, now let's increase the angle. Better, right? Better than before. But now I gotta send this thing to the back, otherwise it's going to... Oh, I have another line here. Ah, interesting. I have another line here. Here you go, that's gonna be my F sub S. I didn't want this guy to... Good. This one I'm going to move like that. To make my right... Oh gosh. I gotta send it to the back. Otherwise it's going to send to the back. What time is that? 5:39. Yeah, good. I send it to the back. Here's my WX now. Okay, this guy, I'm gonna... Let me clean that up. Taking a long time, huh? Okay, I'm gonna clean that up. I increase the angle. Let's see if I can... Nope, not that I want. It's this one that I want. Okay. Oops. Increase the angle. Good. Now this one becomes theta prime because it's greater than theta. IO. Good. Theta prime. This one is going to be ungrouped. Good. Now I can put my weight downwards. Get this weight out of reach here. That's who's gonna be my WX component now. WX component increased because of the angle. Okay. Object in the verge of motion because it's in the verge, object in the verge of motion. In the verge of motion. Calculate the coefficient of static friction, mu sub s. Symbol. Mu sub s. Okay, that's my F sub s. Oh, I made it upside down. Here you go. F sub s. That's the weight. Let me move this one elsewhere. Oops. And that's gonna be my WY perpendicular to the X plane. Here you go. Somewhat like that. So my W sub X should be a little bit longer. Mass, okay. Now I can put my W sub X here. And I can put my W sub Y. Just by changing the angle, that's what it takes, Sometimes I think I should have done by hand. Here you go. That's the normal. M theta prime. Okay, so you already know that this angle is theta, right? According to what we did before. So I'm not going to illustrate that again. Already know that this angle is theta. And now, the equations are similar. It's just the angle that changes. And, okay, I gotta just copy this guy here. Paste it here and change the angle from theta to theta prime. theta prime, theta prime. Okay, and we want to find out the coefficient of static friction. Okay, let's not forget that now, because the object is in the verge of motion, the force of static friction in the x direction coincide with the maximum value of the force of static friction. And if it coincides with the maximum value of the force of static friction, what the value is going to be is going to be that mu sub x, right? Here you go. The coefficient of static friction, mu sub x, mu sub s, not mu sub x, mu sub s, times what? Times n. I'm going to highlight what I want to calculate. Here you go. That's what I want to calculate. I do know the normal. All right, let's go to the next step. I'm going to erase this guy here. I don't need it anymore. Simplify my equation. Substitute mg cosine of theta above. Okay, sometimes you need the second equation, right? Before, in the previous problem, you didn't need the second equation because you're calculating only the force of static friction. And we can finally determine the coefficient of static friction. Mg cancels with mg. Cosine goes to the other side. Okay, we get tangent of theta prime. So that's how we determine the coefficient of, not just the coefficient of static friction, but also the coefficient of kinetic friction by performing this simple experiment. Okay? What time is that? 5:45. We can perform the same calculation for the coefficient of kinetic friction. Now let's take attendance here. Any questions? This guy went slow enough. Maybe too slow, right? So slow that became boring. No? No? Too fast? No? Somewhat? Okay. Let's see, Excel. Let me get attendance here. Are you seeing that for the first time? I'm presuming that you have seen that something like that before, right? Who has seen that something like that before? You have seen that before? Did you learn well at that time? No? Oh, which was that? Physics 11? Which, or Physics High School? Physics 11, right? Yeah. Okay. So let's see. Today is the first. No, today is the 5th. Let me. Yeah, hang in there. Let me erase that. This one. The drawing is the same as you saw before. This one here, right? Okay, here you go. Just a little bit larger angle. Let me make it clear. It's that theta prime here. Do you see how important it is to draw in physics? It doesn't have to be a masterpiece. You know, just something simple like that. Just is enough for you to solve a problem. Okay?
Unless if you have to use like SolidWorks.
Oh yeah, unless you have this huge problem, right? Design a building that you're gonna have a bunch of forces in there,
Yeah,
right?
yeah, you use a lot of measurements.
That's right. Yeah, unless you have something. Yeah. Let's see. Daniel Abraham is not here. No. Mario Acevedo.
Yes.
Good. Harun Atif. Musa Atif. Genesis Bell. Jennifer Camarillo Medina. Okay. Vincent D'Aloisio. Okay. Robert Faust.
Yeah.
Okay. Pedro Flores. Lawrence Flores.
Yeah.
Alexander Garcia. Good. Sung Han. There. Brian Herrera. Okay. Brian Herrera disappeared, huh? Brian Ines. Athena. No. Athena comes for the lab, but she doesn't come for the lecture. Huh? Jesus Lep. Cassandra Martinez. Dylan Martinez. Henry Martinez. Leonardo Melgar. Nope. Leonardo too. He comes for the lab, but he doesn't come for the lecture. Oh, yeah, he comes for the lecture. Rafael Mercado. There. Next, Raymond Miramontes. Jaime Mondragon. Alexis Negret. Yahia Paris. No, she dropped. Marco Antonio Partida. Armando Perez. Abraham Perez. Nope. Nicolas Pisano.
Yeah.
Good. Hans Puster. Nope. Ramon Quintana. Albert Ramirez. Ali. Okay. Amna. Yeda. No. David Son Paxley. Not here. Antonio Vega. Kenneth Villagomez. Patrick Villalvazov. Good. Nolan Williams. Nolan, not here. Let's see how many we have it. 29. Okay, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so I missed someone here. 29. Okay, now we got 21. 551. Break. Let's see, break. I'll write that down right in here. Do you still need the drawing? The girl there? Do you still need the drawing? Okay. Okay, so break from 552, right? To what's that? It's gonna be 6:07. 6:07 p.m. Okay.
Don't you want to stop the recording?
Oh yeah, good. Otherwise, you're gonna have a huge file. Remind me when we come back, right? Pause. Good. We're recording again. Another example. Mass M. You know, sliding with constant velocity on top of a plane with angle theta. Angle theta. Okay. Find the coefficient of kinetic friction. Kinetic friction. Okay. By the way, are those recordings useful? You know, I'm doing that for the first time. Okay, I'm recording those things and putting my internet there for the first time. Are they being useful to you all, folks? Huh?
Yeah,
Yeah. Come on. Yeah. Okay.
because to go over what we missed.
Uh-huh. Take some time, right? I stopped uploading the notes, okay? Because we have the recording there. Do you still need the notes, the PDF notes? You still need? Yeah.
On the test, is it going to be a lot like the lambda sign questions?
Yeah, and you also have to know the the material here, right?
Yeah.
The material here is helpful for you to do the homework and help you, if you go through the material, maybe a couple of times, this 2 or 3 times, because it takes time for you to get all the ins and out. If you know, get to go through this material, the lecture, 2, 3 times, and then you go do the homework, you'll be
Good.
you'll be good for. But don't forget, it's open book, open notes, right? The test is open book, open notes. Yeah,
And it's on the online interface?
yeah, it's gonna be the Canvas.
On Canvas. Okay.
On Canvas, yeah,
Canvas, yeah.
it's gonna be on Canvas. I never did this exam on Canvas for this 24-hour window, okay? But they told me that we can do that and assign 2-hour block. I think it's gonna work. I did for others, other types of. I did for Connect. Yeah, I did for Connect. I gave my students like 24 hours to do their exam in Connect, not in Canvas. Huh? Okay, but the guys at Canvas told me that it works fine. There's no problem. So I don't think there'll be a problem. Have you done that before with other professors in Canvas? Okay, it works, right? Okay, it's easy. Okay, that's good. So here we go. Let's. Yeah, remind me to post those notes, right? So you have something also to study for the exam. I just don't post the PowerPoints. Okay, the PowerPoints I don't post because I consider those proprietary. But you can look at the videos for the illustrations. Let's see. Ah, why is so slow? Yeah, keep on flashing here. Forget it. Oh, finally. Four, find space, single. Good. So now you should save some space. Okay. Solution. I have slide is constant velocity on the top of a plane, inclined plane with angle theta. Change that, find the coefficient of kinetic friction. Symbol. And now we're gonna get, I can use this one. Okay, so here we go. But now the velocity is not zero. Now there is a velocity downhill, which by the way is constant. If the velocity is constant, the net force is gonna be what? Huh? If the velocity is constant, what's gonna be the net force applied to the object? I'm gonna name it theta again. Object not in the verge of motion. Find mu sub k. Now it's in the verge of motion. Now it's already find mu sub k. Now what's that? Okay. And here's not gonna be f sub s. Here's gonna be f sub k. V constant down the hill. And I'm gonna put the same color. So there is no doubt that arrow is associated with constant velocity. Right? I already have the forces are going to be the same. Right? There's no other force here involved. So the equations are going to be similar as well. Any question? No? Okay. So let's go back to the, because it's constant velocity, the net force is going to be what? Okay, I'm going to copy all of that. Yeah, here you go. Solution. Solution. Mass moving with constant velocity, comma, net force must be 0. Okay, weight, normal, and now it's not F sub s, now it's going to be F sub k. Okay, net force along the x direction is going to be 0. Net force along the y direction is going to be 0 as well. Yeah. There is only, let's see, this one is going to be F sub k again. There is no y component for the force of kinetic friction. Just like before, we're repeating the same problem for a different case, but all you gotta do is to change, you know. I can even go a step further and state that Fk in the x direction is equal to F sub k. The x direction becomes redundant. Okay. But what I asked for the coefficient of kinetic friction. Okay, coefficient of kinetic. Now we do not have a maximum value because it's a coefficient of kinetic friction. Kinetic, go. And the coefficient of friction becomes coefficient of kinetic friction. It's no longer theta prime. I define it as a theta. The normal, oops, is gonna be, here we go. And we go ahead substitute n right in here. Take away the prime. Take away the prime. Take away the prime. Take away the prime. Tangent. Okay, and here too. The equation is similar to that of the coefficient of static friction, but the physical situation is the same, because in the case of static friction, the object must be at rest. In the case of kinetic friction, the object must be moving with constant velocity. In both cases, the net force is equal to 0. Okay. Okay. The similarities and differences between this problem and the previous one. Okay. Net force is equal to 0. There's a similarity. Okay. Both results. Oh, don't forget it. That's K, right? K. Both results involve the same equation. Okay. Is equal to 0. Similarly, both results involve the same equation. The similarity. Differences. First case, object must be at rest and on the verge of motion. In the second case, let's put in the case of static friction, object must be at rest and on the verge of motion. In the case of kinetic friction, object must be moving with constant velocity. Okay. Now angles are different. Okay. For the verge, in the case of the verge of motion, I'm gonna use this one here. Go. Angles are different. You know, the angle for the coefficient of kinetic friction in general is less or equal than the angle of static friction. So it's better to put less or equal. Just because the coefficient of kinetic static friction is usually greater. You go. Like that. Another one. Coefficients of friction are usually different. copy that. So those are good similarities and differences to point out. Okay. Save it. Let me, I'm gonna post it right now so I don't forget. It's gonna be a PDF document. It's gonna take some time to, oh man, it's gonna take some time to save, but that's okay. Wait. I'm suspecting that the problem is this guy here, it's too heavy. Let me see if it's gonna go faster. Not responding. That's not a good thing. Yeah. Gotta wait. While he's still thinking. Oh, 2000. Interesting. Oh, that's the slides. Lab notes, P37 notes. That's the one. Let's see if he's still saving it. Yeah, he's still saving it. Okay. And oh gosh, big mistake. I shouldn't have done that. Well, at least give you some time to catch up, right? Let me pause momentarily, okay? Here you go. So far, we applied Newton's law just for motion in one. Let me see how I'm gonna do it. Okay, now let's do that. Okay, now in chapter 6. Now in chapter 6, we will apply Newton's law for circular motion. Okay. I'm gonna need my PowerPoint again. From here, let's see. Not now. Okay, we did that. Okay, that's another type of problem. Here we go, we did that, right? I showed that to you. Those are other types of examples that we have out there. Now we're going to apply Newton's law of motion for circular motion. Let's skip this. Okay. We covered that. Yeah, we did that. Okay. Oh, you know what? We can do that. We can do that one here. Huh. You know what? Let's not do chapter 6 yet. Let's do, let's do chapter 6 later on. Let's do problem of apparent weight. The problem of apparent weight. Why astronauts float there in space, right? So we can explain that using Newton's laws of motion. Let's see, here you go. And that can be explained in terms of the elevator, Okay? So that's the problem of apparent weight. I don't think I have that in my notes. I gotta add that to my notes. Let me see if I have it here. Yeah, I have to add to an example of that to my notes here. I don't see problem of apparent weight here. Okay, I'll do that. Okay, so here we go. Problem of apparent weight. Consider an individual inside an elevator that is at rest. Okay, this individual is on the top of a scale. Okay, inside an elevator. Okay, here you go. I'm not gonna put at rest. Consider an individual inside an elevator. This individual is on the top of a scale. Determine the force the scale register for the following cases. A. The elevator is at rest. B. The elevator is moving upwards with constant velocity. C. The elevator is moving downwards with constant velocity. The elevator is accelerated upwards with a non-constant acceleration. The elevator is accelerated downwards with a non-constant acceleration. All those cases we're going to investigate right now. Okay, so solution. If you're seeing that for the first time, this, what we're seeing here is not going to be obvious, okay? So here you go. Elevator at rest. Let's go make a drawing of the guy on the top of the inside the elevator and on the top of the scale. Apply all the forces. Identify all the forces being applied to the guy, to the individual. Not only you have the weight, but you also have the normal, right? The elevator is at rest. Consequently, the net force applied to this guy must be 0, right? So here you go. elevate. So that's kind of straightforward, the first one. Elevator at rest, net force, elevator at rest, individual at rest, consequently, net force applied to individual must be zero. There are only two forces. There are only two forces applied to individual weight and normal. Now there is a little secret, okay, about this normal force and scales. It happens that, it happens that the normal force is the one that the scale registers. Okay? So if you have a scale that is calibrated to measure force, okay, so whatever is displayed there in your scale is going to be the force, just like the scales here in the States that are calibrated to measure in pounds, right? Pounds is a force. But if I go to Brazil, my scales there in Brazil is calibrated to display the mass of the individual, okay, in kilograms. If I want to know the force, I gotta multiply that by G, which is approximately 10. It's not a difficult calculation to make, right? So here you go. It has that the normal force is the one that the scale registers. So the force in pounds registered by your scale is not only your weight, but also the normal force that you are that the scale is exerting on you. And by the way, because you are interacting with the scale, you are also applying a normal force on the scale downwards, okay? The pair of action and reaction. This weight here is actually a pair of action and reaction at the center of the Earth. But this normal here is a pair of action and reaction right here where the scale is located. I'm gonna put it format shape. Right in here. Okay, and I'm gonna put a dash too. Here we go. So you understand that this is a force that is being applied to the scale, and our system is not the scale, but our system is just this individual here. Okay, and I'm gonna write that down minus n. Minus n right in here. Okay. So what the scale register here is the normal force. Okay? That's the little secret that you have to know. And now that you know that, we can do the other fun things that comes along with this problem. Okay, so here we go. So here we go. I gotta get my equation. What time is that? 6:42. Okay, we have to finish that later on, but let me finish this one at least, right? Net force here you go. Net force is going to be the weight and the normal, and because the individual is at rest, it's going to be equal to 0. So the weight is going to be You know what? I'm gonna put this normal here on the left side. It's gonna be minus the weight. Since the weight is downwards, the normal will have to be upwards. And the weight is mg. Did I say that the individual has a mass m? An individual of mass m, an individual of mass m is on the top of a scale. Determine the force the scale register for the following cases. Here you go. And I'm gonna write that down. Here you go. Normal magnitude of the normal here. And now I'm gonna denote the scalar n as the magnitude, okay? It's mg. Denote like that. Here you go. This one, yeah, looks like that's the one. Yeah, that's the one. So next time we do for constant velocity, but constant velocity is similar, right? For constant velocity, let me just write quickly here. We have 5 more minutes to go. You can do it for the constant velocity. Elevator is moving upwards with constant velocity. Okay, because it's constant velocity, net force is also equal to 0. Here you go. Because it is constant velocity, comma, net force is also 0, whether the constant velocity is upwards or downwards. Moving upwards slash downwards. So it makes no difference whether is at rest or moving with constant velocity. We have the same situation right here. The scale still register the same value. The thing becomes tricky whenever the elevator is accelerated. And that we are going to do next time. Okay? So we're gonna have a lab now, and if you know any of your group partners that didn't come today, please contact them and tell them that we're having lab, okay? And Thursday we have the lecture, right? But we don't have the lab on Thursday. Thursday we have the lecture, but not the lab. Okay, I'm gonna terminate the recording. Good.